Good afternoon, everyone. It is my pleasure today to introduce to you Duccio Macconi, who is a PhD candidate at the University of Bologna. He got his master's degree also at the University of Bologna, and he's working with Dr. Paolo Grandi and Professor Christian Vignali. And he's going to share with us today about his work with radio galaxies and the large scale environment. So Duccio, please take it away.
Thank you so much. Thank you also for the opportunity of giving this talk. I'm Duccio. I'm a PhD student from Italy, from Bologna, and I work on radio galaxies, and in particular on testing the link between the accretion rate onto the supermassive black hole and the power of the produced jets. But first of all, let me briefly introduce AGN, then what is a radio galaxy, and then which is the topic of my work. So basically what I'm interested in. As all you know, at the center of almost all massive galaxies, there is a supermassive black hole. Supermassive meaning from million to billion solar masses. So basically in every massive galaxy, there is a black hole, but in the vast majority of cases is just there. And we call these galaxies as normal or silent. In a small percentage of cases, this at the center, at the very center of some galaxies, if this supermassive black hole is actively accreting matter, an active galactic nucleus can be formed. Active galactic nucleus basically means a bunch of structures that are formed in a very small scale, parsec scale, so tiny compared to the entire scale of the galaxy. A bunch of structures can be formed there, basically accreting structures. And in this tiny volume, so basically matter accreting onto the supermassive black hole, tremendous energies can be produced. In this tiny volume, we can reach 10 to the 48 ergs per second as total luminosity. So incredible energy can be produced there. And in some cases, in some AGN, we also find jets. In some cases, the AGN is able to produce and launch jets, basically relativistic plasma, which is launched up to the speed of light and can reach megaparsec scales. So scales that are 10 hundreds times the scale of the entire host galaxy, not only the central region where the AGN is. We call this kind of objects radio loud AGN. So radio loud AGN are a small percentage of AGN which are able to produce and launch jets, which is relativistic plasma basically. So let me show you which is the main ingredients to build a radio loud AGN. This is a very famous sketch from the one of the first paper by Urri and Padovani in 95 about the AGN unification. These are the basic ingredients of the AGN. As I was saying, this region is about 1 parsec. So there can be a dusty torus, there can be a disk, an accretion disk, which can come in very different flavors, such as it can be thin, efficiently accreting, cold disk, Shakura Sunyaev-like, or it can be thick, hot, ADAF-like. So very different kind of accretion disks. We also have clouds orbitating around the supermassive black holes, which are basically broadline regions, narrowline regions. And in very different scales, obviously this sketch is not the scale, the jets are produced, launched, and can reach megaparsec scales. So million times larger scale than the accreting structure scales. If we look at this object, a radio loud AGN, and we imagine to point toward the jet direction, we will see a point-like source completely overwhelmed by the non-thermal emission. Basically, we are overwhelmed by the jet emission because the jet is pointing toward us, and basically it's plasma which is moving at relativistic speed. So we are completely overwhelmed by its emission. But if we imagine to look at exactly the same flat spectrum radio quasar or BLAC, we imagine to see it in a from a different perspective. So with the jets pointing toward the plane of the sky, in that case, we are observing a radio galaxy. So exactly the same object with another angle seen from another line of sea is a radio galaxy. So as you can imagine, radio galaxies are fundamental to study radio loud AGN in general, because we can study both the accreting region, but we can also distinguish different structures inside the jet. We can have a lot of information about the radio emission of jets, their structures, etc. So let's focus on radio galaxies. And if I should give a definition of a radio galaxy, I would define a radio galaxy as an AGN, radio loud AGN, so able to produce relativistic jets. And these jets are pointing toward the plane of the sky so that we can have information on the jet structures. For example, here you have a very famous radio galaxy, Hercules A, seen in the radio band, obviously. And we can distinguish different features of the radio galaxy. So the radio galaxies are very interesting because we can study both what's going on in the nucleus, so what's going on also in the accreting region, but we can also study what's going on large scales, and how are their jets, how are the jet morphology, the jet power. So they are very interesting objects. But to understand which is my topic, my research activity, what's about, let me spend 2 slides on radio galaxy classification, because they are necessary to understand which is my aim. So obviously, for the first time, radio galaxies historically were classified according to the radio band. This is because obviously the radio emission, the synchrotron emission, on large scale is the most evident feature of these sources. And they were classified by Fanaroff and Riley in 1974 in edge darkened. You can see a right-hand side panel, an example of an edge darkened, also named Fanaroff-Riley type 1. So the bulk of the emission is near the center. And on the other hand, they can be defined as edge brightened. So if the bulk of the emission is far away from the center, usually we see these twin very bright region, point-like regions, which are named hotspots. So FR1 edge darkened, FR2 edge brightened. But soon it became clear that this morphological distinction neatly reflects into a difference in terms of total radio luminosity, with edge darkened FR1 characterized by lower total radio luminosity with respect to edge brightened FR2. So the radio classification basically is about the jet morphology and the jet power. So traces somehow the ejection phenomena in radio galaxies. How is the ejection, how powerful, and which is the morphology of this ejection. Later, in the 90s, radio galaxies were classified also according to their optical emission, and in particular according to their optical spectra coming from their narrow line region. Again, I'm showing to you this sketch from Urri and Padovani. And as you can see, narrow line regions cannot be hidden within the torus. So we always see narrow line regions in AGN, obviously, if they are present. And so according to the narrow line region spectra, we can classify the radio galaxy. Why? Because if the narrow line region are strongly photoionized, there is a bunch of photons coming from the central engine, so basically coming from the accretion disk region, if there are a bunch of photons which are hitting, which are photoionizing narrow line regions, typical lines of high excitation will be produced in narrow line region, emitted in narrow line regions. Conversely, if a low, if this power, photoionizing power coming from the accretion disk is low, we will find typical lines typical of low excitation in narrow line regions. So we can distinguish, exploiting BPT diagrams, we can distinguish radio galaxies according to their narrow line region excitation level, if they have high excitation or low excitation. So basically, depending only on some emitting line ratios. We can distinguish in low excitation radio galaxies and high excitation radio galaxies. And you can see here an example from the 3CR sample. Why it is important, this optical classification? It is important because it reflects basically different accretion rate. So low excitation means low accretion. Again, I want to stress that this is due to the fact that photons which are photoionizing narrow line regions are coming from the central engine. So we can trace if the central engine is efficiently accreting high excitation radio galaxies or as low accretion, low excitation radio galaxies in this case. So the optical classification reflects how efficient is the accretion rate. While I was saying the radio classification reflected how efficient is the ejection phenomena, how powerful are jets. So with these two classification, we can have, I would say, a budget in the sense that we can trace both which is the accretion and which is the power of the produced jets with these two classification. So historically, the classical scheme for radio galaxies is usually when we find inefficiently accreting radio galaxies, so inefficient engines, they are associated with weak jets. And on the other hand, if we see very efficient engines, so very efficient accretion, Shakura-Sunyaev, cold disk, thin disk, usually they are associated with strong jets, powerful jets. Here I report some observational works in this direction, in the direction of finding a connection between the accretion onto the supermassive black hole and the power and the morphology of produced jets. So the classical scheme for radio galaxies is a dichotomy. We have inefficient engines usually associated to weak jets and efficient engines usually associated to strong jets. And we call these kind of objects FR1 LERG versus FR2 HERG, or classical FR1 versus classical FR2. Again, this is supported by both observations and theory. And this is the classical dichotomy, classical scheme for radio galaxies, due to this link between the accretion and jet power. So here is inserted my work, because the problem with this picture, with this simple scheme for radio galaxies, is that there are sources for which they seem to break this classical scheme. Basically, they do not fit into this picture. In fact, for example, there are radio galaxies named FR2 LERG, so they have inefficient engines, low accretion, but they are associated to powerful jets on large scales. Again, here I want to stress that we are talking about the two classifications come from very different scales. The optical classification reach parsec scale, while the radio large scale morphology and power is on 100 to 1000 kiloparsec scales. There exist sources that seem to break this classical dichotomy, this classical scheme. And the most famous sources that do not fit into this picture are FR2 LERG, because they are very common basically in every radio galaxy sample. They are very common, and we basically don't know their nature, why they have this strange behavior. So my topic is to study these kind of objects and to compare these kind of objects with classical FR1 and classical FR2. So have FR2-LERG as my key sample, I would say, and classical FR1 and classical FR2 as control sample to understand which is the difference of these sources. In particular, then we are trying to test this accretion ejection connection that was usually found. So we want to study the nature of these sources that do not fit into this picture and try to understand why they have this behavior. So we are studying radiogalaxies. This is the aim, but the methodology is having a multi-scale approach, in the sense that we want to study, obviously, what's going on in the central engine, because there we find differences. But we want also to study what's going on large scales. If the environment plays some role in shaping radiogalaxies, in deciding their morphology or power. So, with this aim, what I've done at first, as my first step 2 years ago, was to study the 3CR sample, so probably the most famous sample of radiogalaxies, the third revised Cambridge catalog, in the local universe, in particular exploiting X-ray spectral analysis. This is because through X-ray we are able to see what's going on down to parsec scale in the black hole vicinity. So we are able to measure how much gas is available in the central engine and how is the accretion rate there on parsec scale. So we have exploited data from literature, from archives, from different telescopes such as Chandra, XMM, NuSTAR, and we have studied the 3CR sample to understand which is the FR2-LERG nature, why they seem to break this classical connection between accretion, jet power. To explain FR2-LERG nature, we have found, straight to the results, we have found two possibilities in our past work. We have found two possibilities. The first one is that FR2-LERG could be evolved FR2, in the sense that in the past, they were efficiently accreting sources, and so their large-scale radiomorphology and power is the heritage of this strong past accreting activity. But now they are starved. Now their central engine is starved. In fact, if you look at left-hand side histogram, which measure the gas column density from through our X-ray analysis, you can see that FR2-LERG show a lower gas availability than classical FR2. And they are intermediate between FR1 and FR2. So they have less gas, and also the accretion rate is affected, obviously, by the lower gas availability. In fact, if we look from our X-ray analysis to the accretion rate, FR2-LERG show a lower accretion rate level than classical FR2. So basically, this evolutive scenario is FR2-LERG now are evolving in the sense that now they have less gas and they have a lower accretion rate, so they are going to switch off, basically. But this information has not yet reached the large scales, the radio scales, which are on 100,000 kiloparsecs. The second possibility to explain their nature that we have found is that the environment plays the major role, decides everything for FR2-LERG, basically. Let me explain through this plot, this scenario. Here we have on the x-axis the megaparsec scale information. So basically, for each radio galaxies, we are able to measure how many galaxies are there within 1 megaparsec from each radio galaxy. So we are able to measure how crowded is their environment, how dense is their environment within 1 megaparsec, which is typical scale of cluster of galaxies. So we can define how rich and how poor is their environment. So megaparsec scale information, x-axis. On the y-axis, we have the accretion rate information. So here we are on parsec scale. So there are 6 orders of magnitude between x-axis and y-axis. And we find this general anticorrelation in our 3CR sample. General anticorrelation in the sense that FR2, which show the highest accretion, are associated to the poorest environment, while FR1, which show the lowest accretion, are associated to richest environment. And FR2 LERG are intermediate. So this possibility, this environmental possibility, says that the environment drives the accretion and then drives the shaping of radiogalaxies, deciding the jet morphology and power. So we want to disentangle between these two possibilities we have proposed 2 years ago. And this is what I'm doing now, trying to disentangle to understand which is the real FR2 LERG nature, if it's driven by evolution or environment. We are doing this and try to disentangle between these two scenarios. We are doing this, expanding the sample to other samples in the local universe, also in the local universe, but reaching lower flux densities. This is because the 3CR sample is a radio-selected sample with the Jansky flux density limit. But now there are plenty of new survey in the milli-Jansky sky, so with sources 1,000 times fainter in the radio band. You can visualize this concept here because in the same redshift range, the 3CR below redshift 0.3, the 3CR can be considered only the tip of the iceberg, because in the last years, a lot of radio galaxy samples were built in the milli-Jansky sky. You can see in the right-hand side panel, basically the same information. We have the redshift versus flux density, and you can see 3CR is only above 1 Jansky, while, for example, Beste-Ekman is has a lot of sources below this threshold. So we can, going in the milli-Jansky sky, we can increase a lot the number of sources, stay in the same redshift range, and study what's going on fainter sources. So basically, we have built, what I'm showing today is our last sample that was built starting from Beste-Ekman sample, so starting from SDSS survey. So we have, for each radio galaxy in this sample, we have the optical spectrum. But then there were a lot of work associated to SDSS survey, which studied also the large scale environment of these sources. And there are a lot of different information for these sources. So we have information on parsec scale, because we can have the accreting region information, the lines coming from the central engine. We can have host galaxy information, given again the fact that we have the SDSS spectra, and we can also have large scale information. So how, in which environment these galaxies live, only taking into account samples that are already in literature, starting from the SDSS survey and matching different samples. We are able to build a huge sample of 8,000 radio galaxies. I want to show you the sample distribution in terms of redshift range. Again, it is in the same redshift range as the 3CR, but the fluxes, as you can see, the radio fluxes are really below the threshold of 1 Jansky. And as you can see, we can distinguish sources for this 8,000 sample. We can distinguish radio galaxies that are isolated and radio galaxies that are in cluster environment, according to their megaparsec scale number of companion again. So let's focus on this sample. And let's try to understand at first, which is the role of the environment indirectly shaping the radiomorphology and radio power. So let's study the megaparsec scale environment. So if they are isolated in cluster, considering if this large scale environment is directly modifying their radiomorphology and power. So at first, let me show you the percentage of sources that we find, the radio galaxies obviously, that we find in field, so isolated. The number of radio galaxies in isolated environment is 5,000 sources, and we have 25% of FR1 and 9% of FR2. If we go in cluster, we find 3,000 sources, and we have 34% of FR1 and 60% of FR2. So I want to stress that both percentages are increasing, passing from isolated to rich environments. So there is no environmental segregation for the radiomorphology of radio galaxies. They both increase, passing from isolated to rich environments. Again, if we consider only sources in cluster, we can again trace which is their cluster richness. So basically, how many galaxy companion each radio galaxy has within 1 megaparsec. As you can see, FR1 versus FR2 show a very similar distribution in terms of cluster richness. There is no huge difference. Also, if we, for example, we consider the Kolmogorov-Smirnov test, which is basically a statistical test that measures how much two samples are different, which is the probability that two samples come from a different distribution. And the probability in this case is very small, 10%. They show very similar cluster richness. Also, if we consider right-hand side panel, the distance from the cluster center, FR1 versus FR2, again, with 0 is where 0 is the cluster center, basically, and 1.0 corresponds to the cluster radius. So we can see where these radio galaxies, when found in cluster, where they are, if they are in the cluster center, in the cluster outskirts. And as you can see, the vast majority of sources are in the cluster center. 70% of them are in the cluster center. Remember this because later I will show you that sources in cluster have higher black hole masses, but this is obvious because the vast majority of them are in the cluster center, where in the cluster center we find the largest galaxies in the universe and the largest black holes in the universe. But only considering the environment, then their radiomorphology seems not to be shaped by a large-scale environment because their percentage, as I was saying, is increasing for both FR1 and FR2 from field to cluster. The cluster richness when sources are found in cluster is similar, and also the distance from the cluster center is similar. So we do not see any difference in shaping radio galaxies depending directly on the environment. So let's discuss the first scenario. FR2 LERG are evolving sources. Let's, for the moment, exclude the second scenario and focus on the first one. Again, I want to stress that FR2 LERG, we found in the 3CR that FR2 LERG are intermediate in terms of gas availability and accretion rate between FR1 and FR2. And I want to stress that the evolution should go from HERG to LERG, from high gas column density to low gas column density. In fact, FR2 LERG, they have strong jets on large scales, which are the heritage of a strong activity. So the evolution is from HERG to LERG. Let's test this. Let's test HERG versus LERG in terms of black hole masses to see if we are in agreement with this evolution from HERG to LERG. So let's test different engines, which is the difference in terms of black hole. At first, I already said to you that in cluster, we find larger black hole masses than in field. And this is, again, is not surprising since the vast majority of sources in cluster are at the cluster center, where we find the largest galaxies in the universe. So this is not surprising. The most interesting thing is to compare HERG versus LERG in isolated and cluster environments. As you can see, in both cases, the result here is really clear. HERG always, independently from the environment, show a lower black hole masses than LERG. LERG are always more massive than HERG in terms of black hole. And as you can see, the Kolmogorov-Smirnov probability are above 99.9%, so they are distinguishable. And then the HERG to LERG evolution is supported, because as you know, the black hole can only increase its mass. So this is in agreement with what we found in 3CR, and is in agreement with HERG-LERG evolution. So let's test the large-scale environment, which is its role on the central engine, so on the HERG-LERG definition. And as you can see, the percentages of sources passing from isolated to rich environment, LERG increased their number from 67% to 82%, while HERG are decreasing their percentage. So here, there seems to be an environmental segregation. But what this segregation about? This is about the fact that in cluster we find larger black hole masses, larger galaxies, because the vast majority of them are at the cluster center. And then maybe we are finding more evolved sources in the cluster. So LERG-like, again, the evolution is from HERG to LERG in our perspective. So again, in the richer environment, where we find more evolved and larger galaxies, we find more LERG sources than HERG. This is true also considering only sources in cluster. So if we compare LERG versus HERG in cluster, and we see which is their cluster richness, we can see that they are different. Also, when found in cluster, HERG are found in poorer cluster than LERG, with a large probability again. Again, considering the distance from the cluster center, LERG are 70% again found in the cluster center, while HERG has a not negligible tail on the cluster outskirts. So again, the cluster, again, for the black hole mass, and also for this reason, the cluster seems to be favorable to evolved sources, LERG-like sources, instead of HERG. While HERG are more common in field, and they have a lower black hole masses on average. So, to test again this HERG-LERG evolution, let's consider what's going on the host galaxy scale. So what's going on in the host galaxy of this kind of objects? Here I report the calcium break histogram. Calcium break basically is can be considered an estimate of how old are the stars within a galaxy. Calcium break basically is a measure at 4,000 angstrom in the optical spectrum then from the host galaxy, so it's a property of the stars, that basically it is a break at 4,000 angstrom due to the fact that below 4,000 angstrom there are a bunch of calcium absorption line. So the more the galaxies evolve, the more the galaxy is not forming stars and it's old, the more this break is found to be high. As you can see in the right-hand side histogram, red and dead galaxies, so basically early type, red and dead, have typical values of 2.0 as calcium break, while late type sources show smaller values. So basically, calcium break can be considered a proxy of how old are the stars in the galaxy. So let's compare LERG versus HERG in terms of host galaxy properties, so kiloparsec scale, tens of kiloparsec in the x-axis, versus accretion proxy, calculated from the oxygen tree line luminosity, so parsec scale information on the y-axis. And as you can see, the vast majority of LERG are here, red and dead region, low accretion, while HERG span a wide range of values. But then I want to show you also this contour plot, because I want to introduce the contour plot because the very last slide, the next one that I will show you is about a contour plot, because I want to visualize, I want to show which are the characteristical regions for some kind of radio galaxies when they are most probably found. So you can see this is exactly the same plot, left-hand side and right-hand side. Left-hand side, we have marks, right-hand side, we have the contours. So basically the contours are about how many, which are the more dense regions. So what I want to show you the same, exactly the same plot. So kiloparsec scale information, how old are the stars, versus accretion rate information, only for LERG. Because as I was saying, LERG span a wide range of values here, really. So I want to show you if there are differences within LERG. So let's test LERG FR1 versus FR2, same plot, calcium break, kiloparsec scale versus accretion, parsec scale. FR1 LERG are found to be very similar, both in cluster and in field. They are found to be evolved sources, so with very red and dead, basically, galaxies, and low accretion rate in both environments. In our interpretation, this could be due to the fact that they are the last link of the evolutive chain. So we cannot see differences even in different environments, with different environments that I already showed to you that that are different, that show different evolution. But since these kind of objects are very evolved, are the last link of the chain, we cannot see any difference between cluster and field. They are very evolved in both environments. Conversely, it's very interesting to do exactly the same plot, but for FR2 LERG, because in this case, we can see a difference. This can be considered, this plot basically is a summary of everything I said, because there are a lot of information here. FR2 LERG, as I was saying, show a different behavior in field versus cluster. Again, I already showed to you that in cluster we find more evolved sources. In fact, FR2 LERG in cluster, they are in red here, are very similar to FR1, in both host galaxy stars, and accretion rate. So in cluster, we can see very evolved FR2, in agreement with the fact that in cluster, in general, we find more evolved sources. But if we look at FR2 LERG in field, in isolated environments, we can see that they show a wider range of values, both in terms of accretion and the host galaxy properties. So what we can say is that FR2 LERG are evolving sources. And they are more evolved in cluster than in field. But the evolution of radiogalaxies, which again should be from HERG to LERG, depends on the initial condition, obviously, on the environment, and also on the black hole mass. So I'm collaborating with Professor David Garofalo, which has developed a very interesting theoretical evolutive models for radio Loud AGN to test if my data are in agreement, I would say, with his model, and if we can use our data, we can interpret our data in terms of his model. And his evolutive model is both in HERG, LERG direction, and also from FR2 to FR1 evolution. So we are doing this, and we are trying to interpret these observational results with his theoretical model. Okay, this is just a summary of what I found for this large sample of radiogalaxies, but basically the take-home message is that we have found an evolution from HERG to LERG, and which depends on black hole mass, on the initial condition, and the environment. But since I'm running out of time, I want to thank you so much for the attention, and every suggestion, comment, or question is welcome. Thank you.
Thank you so much, Duccio. Very, very interesting work. So we have time for some questions. So if you would like to ask a question to Duccio, please raise your hand and I'll call on you. Yeah. Oh, yes. Could you put the conclusion slide back up?
Okay, yeah.
Great. Yeah. Okay. Any questions? I have quite a few, so, but I'll see if anybody else has questions before I get into mine. Okay, since no one has raised their hand, so I was wondering, so you generally find that these FR2 LERGs, in the beginning you were saying that you think they were starved perhaps of fuel and such. I was wondering if you had any thoughts on the mechanisms by which that would happen. I asked this because I'm looking into radio AGN activity in merging cluster environments, and I'm kind of finding the opposite in that it seems that in merging clusters that can actually increase the AGN activity. So I was wondering what you were thinking might be the mechanisms for, I guess, quenching the fuel, specifically for the FR2 LERGs.
Yeah, it's a very good point. And I don't really have a model of this switch from HERG to LERG, but the point is that from what we see, it seems that they are experimenting lower cold gas availability. So maybe it is just all the structures of the AGN, so the accretion disk and torus, etc. We are seeing that there is less gas, then the accretion is going low, and then this low gas availability also changes the accretion mode from cold efficient accretion, Shakura-Sunyaev-like, to hot inefficient accretion. So ADAF-like, I would say. So maybe the point is that the leakage of gas availability there in the low fuel, I would say, is changing the accretion mode on parsec scales.
Yeah.
So
makes sense. Yeah, it's interesting. Yeah, I think also, you have the hot gas in clusters, which can, evaporate fueling, just fuel.
Yeah, should be another point of view interesting.
Yeah. I was also wondering, so you found with your newer sample, you had quite a large fraction that were BCGs that were
Yeah,
both HERGs and LERGs. I
yeah.
was wondering if you looked into here, this analysis at the end, if you also had separated according to whether they were the BCG or not. I was just wondering if they perhaps had a different behavior, even being in the absolute center, you know, or really close to the center versus being in the outskirts of a cluster.
Yeah, the vast majority are actually BCGs.
Okay, they are, yeah.
Both because, okay, they are found in the cluster center, but mainly because they have very large black hole masses.
Mm-hmm.
So, and they also have obviously very large stellar host galaxies mass. So they actually are BCGs.
Mm-hmm.
And in that cases, the vast majority of them are LERG.
Okay, yeah.
We can find also some HERG, which they could be very interesting to be studied individually, these HERG that are BCGs, because we expect that BCGs of local clusters should be very evolved galaxies, I think. And then it could be very interesting to study these BCGs that are found to be HERG.
Mm-hmm. Yeah.
Yeah, they are a small number, so I think a follow-up in this direction is possible.
Yeah, I just think it would be really interesting to study that, even though there aren't that many that are not BCGs, I think it could be interesting to see if there are any differences in their behavior, perhaps. Yeah.
According to the mass, I would say that vast majority are BCGs when we find in the cluster center, obviously.
Yeah, okay. Does anyone else have any questions? I do have one final one. So I think it's a slide near here. You had the separation by HERG and LERG and the black hole mass in the field versus, right. So I was wondering if, isn't this rather expected though? Because as you were saying, LERGs are mostly in clusters, and so they're most likely going to be very massive. So I was wondering, isn't that what we're seeing here, or is there some other effect that can explain the separation?
Yeah, but also if we consider separately sources in field and in cluster, we find that LERG are always more massive on average than HERG. So also in field, and they have a large probability that they are distinguishable. So this is in agreement with the HERG-LERG evolution, because we always find LERG with larger masses, independently from the environment. So both in cluster and in field.
Okay, yes, I see. That makes sense. Thanks for that. Okay. Seeing as there are no other questions, thank you so much, Duccio, for taking time to share your very interesting